Welcome to our lectures on NPTEL lectures on advanced power electronics and control. Today we shall continue with the space vector modulations we have started in the previous class. There we shall see a different type of direct AC to or indirect AC to AC conversion technique. So, we have already discussed actually depending on the switches, please refer to our previous discussions. So, we can actually you have a 3 phase voltages, and you know that actually we can represent in terms of polar coordinate, that is some resultant vector and theta, and this is the reference you require to generate, and you will be generating with the switches. When actually it is POO, that means your first leg is switched on and other two leg is lower switch is on. So, PPP we have discussed and OOO are the two null vector. PPPP means all the upper switch is on and OOO means all the lower switch is on. Now, now if you wish to get a VA totally, then you will apply POO. If you wish to get minus VA, you will apply basically the voltage of OPP. Similarly, 120 degree apart, the phase B, you can apply 010 or OPO. Similarly, after 120 degree apart, so these are actually the all actually line voltages. So, OOP, and thereafter actually if you all these three are positive voltages, and if it is VA, if you write it will be minus VA. Similarly, if you write this one as plus VB, it will be minus VB. Similarly, if you write it is plus VC, it will be minus VC. Now, you have to identify a sector and accordingly the switching will be done. So, for this reason to generate these voltages, it can be in any coordinate. V1 to V6 are the active vectors and they are stationary vector, they are not rotating vector, mind it. Rotating vector is your actually the reference, and we shall take a snapshot. During the snapshot we shall consider that V reference and this theta is actually the constant. So, we have actually identified 6 sectors. This is sector 1, sector 2, sector 3, sector 4, sector 5, sector 6, and so they have a 6 active vector and thereafter a 0 vector, and reduce redundant switching states are PPP, then all the switching states are on, and 000 or OOO, all the lower switches are on. Now, we know that actually for 3 phase COR system, what is the basic of actually putting this VREF and these things, because you know that we have only all this VAO, VBO, VCO, it is if it is a 3 phase 3 wire system, instantaneous value will be equal to 0, and we shall convert 3 phase to 2 phase conversion. What we have done actually resolve of force for 2 perpendicular coordinate, it is the same thing. So, this is be your stationary alpha beta frame, and this will be the transformations, that will be the 3 phase to 2 phase transformation. And once we get these transformations, we can write like this, that is Vt equal to V alpha plus J V beta. So, and we should align one of the vector with the vector alpha. V1 can be aligned with the vector alpha and 90 degree to be it will be the J beta. So, this kind of polar representation is valid by it can be established by this theory. So, we can write essentially the reference vector equal to V alpha plus j V theta, or it can have a polar representation under root of V square alpha plus plus actually V r will be actually underscore of V alpha square plus V beta square. Similarly, so V t can be actually inverse transform, that is 2 by 3 VAO in actually VBO e to the power plus 120 degree and VCO e to the power 240 degree or minus 120 degree. Now, you see this. Please recall in our previous classes actually upper 3 switches class A, B, C are S3, 5, S1, S3, S5, and that will be represented here as all the positive phase on, that is PPP, and ultimately you will get a null vector. And once all the lower switches are on, that means 0 0 0 or 0 that is S4, S6 and S2, you will get essentially also the 0 voltage. The switching state, let us see that what happened in a switching state when it is POO, that when you were here. So, essentially what does it signify? From the upper part of the inverter, S1 will be on, S6 and S2 will be on. So, once upper part of the switch is on, VAO will be 2/3 of VDC, you can actually draw the geometry, and VOB will be actually 1/3 of VD, and similarly VCO will be 1/3 of VD. You can add and you get a 0 voltage. And so, V1 essentially we can write that this axis also you can write D axis if you rotate it. So, we can write that is V1 equal to 2 by 3rd VD into angle is basically 0, you have aligned alpha with this reference. So, similarly for any vector you can have, that is if it is a second vector k equal to 1 to 6 here will be 2/3 VD e to the power j k minus 1 pi by 3, where k can take any value 0 to 1 to 6. So, similarly you can, this vector has been explained. Similarly, the opposite will be this vector. Then what will happen? You will find that actually S4 is on from the lower side and S3 and S5 are on from the upper side. So, here essentially you will get in these combinations V4 will be actually VAO will be minus 2 VD, and other two values will be actually VBO will be again 1/3 VD and VCO also will be 1/3 VD. So, in this way all the voltages can be calculated. So, then our task is basically to find it out the theta, and thereafter the theta and this theta and the V reference will be told to you. Our task will to find it out which vector will be applied to generate this voltage state or whatever the electrical quantity you are asking. So, we can have a polar substitutions and we will write V ref equal to V ref e to the power j theta and rotating space omega equal to 2 pi f, the angular displacement theta t equal to 0 to t omega dt. So, you can actually integrate and we can find it out what is the value of theta. Now, you can see if you that actually V ref actually this angle is theta and this is being actually can be manufactured by the combination of V1 and V2. And for some instant of the time, let us say T1 or Ta, so V1 will be applied, and another portion of the time actually let us say Tb, so you will apply the voltage V2, and rest of the combinations, then you have to apply the null vector to fill this actually filler of Ts. So, let us find it out the relationship between Vref and VAB. Vref is approximated by two active vectors and a combination of the 0 vectors, 1 or actually PPP or 000. Vref rotates 1 revolutions and VAB completes 1 cycles. So, length of Vref corresponds to the magnitude of VAB. Now, see that then we shall go for the Bode balance method, that means basically you are balancing the flux. So, Vref into Ts we can write that should be equal to V1 into Ta plus V2 into Tb, and rest of the time you will apply the null vector to balance the value of the Ts. So, Ts equal to Ta plus Tb, and rest of the time you will be applying a null vector. So, Ta and Ta, Tb and T0 dual time for V1, V2 and V0, where Ts is the sampling time. So, it can be actually 100 microsecond. Let us say if it is actually, if your switching frequency is 10 kilohertz, it can be 100 microseconds. Ta can be actually 30 microsecond, it can be 40 microsecond, 30 plus 40 70, and rest of these things will be the null vector, that is also will be the 30 microsecond, that is something like that. So, Vref equal to Vref e to the power j theta, we know that actually it is V1 2/3 of the DC link voltage, and this value essentially will be 0. So, we have to take the imaginary and the real part into the account, and we have to balance it. So, real part or in an alpha axis, Vref cos theta into Ts should be equal to 2/3 Vd into Ta, plus you can see that how this component has been made. So, you will have 1/3 of Vd Tv. Similarly, for the y axis you have to take a component of it. So, in y axis what you can see that it is essentially it is made by only these vectors, there is no entity of this V1 across the beta axis. So, for this reason Vref sin beta into Ts will be 1/3 Vd into Tv. It is a simple mathematics, actually this is this angle in 60 degree. So, you can, if you have a take a projection, it is sin 60. So, the Ta essentially if you can substitute, you can find it out. So, √3 Ts Vref by Vd into sin 60 minus theta, and Tv will be equal to √3 Ts Vref by Vd sin theta. So, ultimately you get T0 equal to Ts minus Tb minus Ta. So, that will be actually the amount of duration when null vector is applied. It is a very simple problem. You will be given this actually the Vref value and the angle, you require to find it out Ta Tb. So, Vref location versus dual timing, how you will actually switch it on, this is one of the requirement you have to keep in mind. Now, you have seen that actually Ta equal to Ts, we say actually this one is something like sine angle modulation, that is √3 Vref by Vd as a modulation index. So, this is actually modulation index of phase A, and this is a modulation index of Ma sin theta, and this is the basically the value of the T0. So, what you can see here, you can actually split it till 30 degree, okay, it is quite clear. So, your this will be the vector actually will be contributed more till 30 degree. So, T A will be more and T B equal to T A equal to greater than 0 and T B equal to 0 for actually if your reference is aligned with the alpha axis. Now, till 30 degree till actually till this reference generally T A is greater than T B. At 30 degree T A equal to T B because it is a perpendicular bisector. So, both the vector will have a same value. Then 30 to 45 degree basically T B is greater than T A, and at 60 degree definitely all those things will be made by T B, there should not be any component of T A. Now, modulation index range, we have talked about the saturations of this modulation index over modulations, because you know that actually over modulation, if you have a square wave, that is over modulation, and you get the value of 4 Vm by pi, and thereafter you can increase this value with the injection of the third harmonic. And one of the basic advantage I have discussed with the space vector modulation is that it is equivalent to the third harmonic, but with the less stress across the switches. So, what can be the maximum Vref max? So, you know that this is basically 2/3 of the receiver's voltage into actually root 3 by 2. So, this value can be Vd by root 3, and so modulation index max can be 1 and modulation index can be actually 0 to 1, and effectively you can see that you can have the value of Vd by root 3 as effective Vmax value. So, this is the value you can generate by your space vector modulation. But very simple thing actually, you have to divide it by 1.732, that is around 60%. So, now let us understand what should be the switching sequence, and their starting point has a great importance. You consider that your starting point was OOO, that means all the lower switches are on, and you recall that you have a actually reference vector, this is V1 and this is V2, you will be generating with POO, and this you will be generating by 0 PO. Now, see that what will happen. If you go back, you see that this voltage is PPO. So, let us mark it actually PPO. So, same voltage vector has been chosen here. Now, actually you have started from the 0 0 0, then definitely your 1 bit change will be actually POO. So, you can go here. So, thereafter you can have a 1 bit change, then you will be here. So, PPO. Then once this is for TA and this is for the TB, now you have to apply null vector. Of course, if you go to actually OO, there will be a 2 bit change, you will apply PPPP. This is also a null vector. Then again, instead of actually starting from V1, this since it is a 1 bit change, you will go for PPO. So, your computational burden will be reduced. Thereafter POO, thereafter 0 0. So, both the cycle will be combined. Since you are actually operating, your switching frequency is at least 50 times more than your supply frequency. Like if you have a 50 hertz, it is your supply frequency is a 50 hertz that you want to mimic, and your switching frequency should be around 250 2.5 kilohertz. So, within the 2-3 instant you can take that reference as a constant. So, similarly for Vn, you know, you, actually this phase will be on for these durations. So, once this switch is on second bit or MSB, then only this voltage will be on, and that continue till that point PPO. Once it again go to the P00, it will go back, and phase C will come into the picture for this very small duration, when actually PPP all the upper switches are on, and this is the way. So, this is the duration has been splitted. You will give the durations T0 by 4 for 000 and Ta by 2 here, Tb by 2 here, thereafter T0 by 2 in these durations, thereafter Tb by 2, Ta by 2 and Ta. So, total will be the total cycle can be generated by this. Now, the basic requirement is to minimize the number of the switching per sampling period. If you actually switch this state to this state, what will happen? You will have a more switching losses. We require to reduce the switching losses. For this reason, one bit change, that means one switching transitions, if you can achieve, that will try to reduce your switching losses. The number of switchings per sampling period is Ts. Implementation transition from one switching state to the next switching state involves only 2 switches in the same inverter leg. So, that if you can ensure, the number of switching state is also reduced and switching losses will be also reduced. Now, see that this is an example of the undesirable switching. If the V1 and V2 are swapped, see there is no change in phase A because it was on for continuous durations. So, first you have a null vector 0 0 0, thereafter it is PPO. So, Van will be 1 or high and continue till this time. So, again the second will be high for this duration, again there it is off, again it is on, again it is unnecessary toggling in between, and thus it will give rise to the high switching losses, and Vd will be given, actually the phase C will remain same. So, total here switching is basically the 10. If you go to the previous slide, total switches is 6. So, it is 4 times more switching has been done. So, almost 60% more will be the switching losses if you have a undesirable switching. So, for this reason, switching sequence has been presented here. So, for if it is actually 0 0 0, you should go to POO and thereafter PPO, thereafter PPP, thereafter it will be again PPO, thereafter POO, thereafter 0 0 0. So, this will be the sequence. Similarly, if you start with basically 0 0 0, if you are in a sector 2, switching logic will be OPO, thereafter PPO, thereafter PPP, thereafter PPO, thereafter OPO, thereafter OO. Similarly, in the third sector, you start with the same OO, thereafter OPO, that is same, but this will change. So, previously it was PPO, that here will be OPP, thereafter PPP, again the mirror image will be followed. Similarly, this way all the sequence has been, or if you are in a particular sector, particular sequence you require to follow to minimize the switching state. We can achieve with the 6 switching only in a whole cycle. So, you see that example. So, this is the basically the sectors, and this is the sector 5, sector 6, thereafter sector 1, sector 2 and so on. This is the way your switching changes, and this is the VAB, and this is the VD voltages, actually the decelerating voltages, and this is the VAO, and this will be your actually the line voltages, and you can see that modulation index is basically 0.69 around 70%, and TS is 1.1 millisecond, and frequency is just close to 1 kilohertz, that is 900 hertz. So, you will get this kind of results. So, what will be this? So, how can you eliminate this? The questions arise, how can you eliminate the even order harmonics? That is, generally you have seen that due to the symmetry that does not present. So, you can be actually eliminate in a two way. That first take the sequence A. So, sequence A, so you have actually you have a logic like you want to generate VAB, you start with the 0 0 0, thereafter OPP, thereafter OOP, thereafter OPP, thereafter all the sequence will come, and you can see that actually this starts and ends with basically the 0 and this side also 0. And here there is another sequence, this starts with the P and ends with the P. So, can you infer anything from these two logics? So, if you start this pattern, so what are the switching states? So, this is the OPP, that this is a BAN, this is the CEN, that what you had got in this actually the first case, but actually here A phase is actually less content and C phase is a more content, and thus AB you will get this kind of sequence, and it is unnecessarily switching. Same logic, you know, if you start with this way PP, then end with the PP, then you will get actually less switching, and this starts and ends with the actually all the positive cycle. Now, even order harmonic elimination, please go back, this is the sequence A. So, you start with 0 0 0, we say that it is a sequence A, and you start with actually PPP or 1 1 1, that we will say that it is sequence 2. Now, see that actually this hashed is sequence B and this part is sequence A, and you will find that this line, this THT line, and you have to have a combinations of odd even harmonic eliminations by A here, then A here. So, B here, then B here, C here. So, this has to be this way combined. So, what happened, you require to operate in a sequence A, you cannot mix sequence A or sequence B, then what will happen, you cannot eliminate harmonics, even order harmonics. And you know, you can see that how this ratio, if it is actually reduced, THT has been actually reduced. So, this is the modulation index. So, if you increase the modulation THT will increase. This is the first fundamental increase linearly, and these are the actually 7 5, because it is a 3 phase 3 wire system. Your harmonic content will be 6 n minus 1, and you will find that these are the harmonic content. This analysis is done for the 60 hertz and for the sampling frequency of this much. So, please note that we require to eliminate the even order harmonic. So, we cannot combine the A or B sequence state. If you wish, you can go for the sequence state A or sequence state B. So, then only you will find due to the symmetry, you know, there is, you can go back, there is a symmetry. So, due to this symmetry, you know, all this odd harmonic will be all the even harmonic will be vanish. But here this symmetry is actually missing. You have a, if you see this line, it has a symmetry. So, for this reason actually we will have all the even harmonic present into the system. Thank you for your attention. I shall continue with the few part left in the actually space vector modulation technique in our next class. Thank you.